I really thank you for the invitation. This is the one that I'm presenting here is a joint work with two colleagues of mine, Raffaella Coppier and Elisabetta Michetti, both of them from the University of Macerata. And this is a work which is part of an Italian PRIN project titled Tax Evasion and Corruption, Theoretical Models and Empirical Studies. So it deals mainly with tax fraud, but Benford law is a powerful instrument that can be used more in general to cope also with different kind of frauds. So I will start by briefly introducing Benford law. Then I will move to explaining how it can help in fraud detection. And I will finish with our application to using Benford law to discover firms' tax evasion in Italy. So I will start with some real data because Benford law actually was formulated after the observation of some particular behavior of a real data set, something concerning the first leading digit in a real data set, where for first leading digit, we mean the first digit from the left in a number. So that, for example, in the number 23, the first leading digit is 2. In the number 0.31 will be 3, so that we drop the 0, we don't consider the zeros. In minus 1.5, it will be 1. So here we have 3 different data sets, just for making an example. We have the first data, which are about populations in different countries. Then we have the area of different countries and the GDP of these countries. And we are looking just at the first leading digit. So we are counting how many times, for example, we observe 1, how many times we observe 2, and so on up to 9. And we can make a plot, a bar plot of the distribution of the first leading digit. So each of these bar plot is for one of the 3 data sets seen before. And we can see that the 3 distributions are very similar to each other, and above all are far from a uniform distribution. We might think that one has the same probability of 2 or of 9 to occur as first digit in a number. But this is not the case. Small digit in real data set have a much larger probability of occurrence than large digit. And in particular, for example, the digit 1 has a probability of around 30% to appear, while the digit 9 has a much lower probability, less than 1%, 10%. So this empirical observation was formalized into a probabilistic law for the first time by Newcomb in 1881, and then later it was made famous by Benford, from which it takes the name. But it is also known as the Newcomb-Benford law, or the law of anomalous numbers, or still the first digit law. So you can find it under many different names. And from a probabilistic point of view, it states that the probability of observing a certain digit D, where D is in the within 1 to 9, the probability of observing D as a first leading digit is given by the logarithm base 10 of D plus 1 minus the logarithm base 10 of D, or in other words, logarithm in base 10 of 1 plus 1 over D. So for example, if we take D equal to 1, here we have the logarithm of 2, which is around 30%. So here I show you the same distribution as before, but I superimposed the theoretical distribution according to the Benford law. So you can see that there is a good correspondence between the observed distribution and the theoretical one, meaning in all the three cases, meaning that the Benford law is able to approximate the distribution of the first leading digit in plenty of different sets of data. So not only data on population like the one we've seen, population of the cities or population of the countries, but also different kinds of data, geophysical data, scientific data, and what we are most interested in, it applies to financial and economic data. So for example, stock prices have been observed to conform to Benford law, or transaction volumes, or what we are interested in, invoice amounts, or also GDP. So it applies to plenty of different data sets. So how can we use this law to help in detecting fraud in general, or tax evasion in the particular case of our work? Many real data obey Benford law, but actually fake data do not obey this law. And this is because if data are manipulated, certain digits might be overrepresented or underrepresented. And so we might observe significant deviation of the observed distribution from the theoretical one, the one under the Benford law. So in practice, we need to measure the distance between the observed distribution of the first digit in the data we are considering, and the theoretical distribution under the Benford law. So to do this, I will introduce some very simple notation. So ND is the number of times that the digit D is observed as a first leading digit. PD is the corresponding relative frequency of occurrences. That means the number of occurrences divided by the sample size. And pi d is the theoretical proportion of times that the first digit D is expected to occur according to the Benford law. So we can develop different measure of non-conformity with the Benford law, and I'll show you here just three of them very often used. The first one is the chi-square statistic, which is simply the sum of the square differences between the observed number of occurrences and the theoretical one under the Benford law, divided by the theoretical one. And if data have not been manipulated, if data conform to Benford law, this statistic has a distribution, which is the chi-square distribution. And so we can use a statistical table to find a threshold above which we can conclude that if we observe a chi-square statistic above this threshold, we can conclude that the observed data do not conform to Benford law. And so this might suggest that data have been manipulated. Another possibility is to use the mean absolute deviation, which is simply the mean of the distance between the theoretical, the observed relative frequencies and the corresponding theoretical probabilities. or still we might use the sum of square deviation, which is not the mean, but it's the sum, and we are squaring the distance. So just to give you some few examples of successful applications of the Benford law in the past. For example, the financial advisor Wesley Rhodes was convicted of defrauding investors after that the statements that he sent them failed to conform to the Benford law. And after a closer examination, it was found that he actually had faked the data. Another interesting application was to reveal false Twitter accounts. So it can be shown that the followers of a given Twitter account should conform to Benford law. If they do not, this means that the account is probably a fake one. Or still, Benford law has been used to claim that the Iranian presidential election in 2009 was rigged, or that Greece manipulated macroeconomic data in its application to join the Eurozone. So this are just some past application. I will show you our application to discovering tax evasion. This is a huge problem in Italy. Everyone of us knows it, so no need to speak too much about it. I just give you some data here. In 2021, tax and contribution evasion amounted to something like 83.6 billion euros. And most of it, 73 billion, was from lost tax revenues. And tax evasion is mainly, the most of tax evasion is due to firm tax evasion. So obviously the main instrument, the principal tool available to tax authorities to enforce compliance of firm is that of auditing and fining in case of evasion. However, the problem is that auditing firm is an expensive and time-consuming operation, so it would be really helpful to have instruments which could target auditing. And our idea is to try and use Benford law as a support in targeting auditing firms' auditing. And we tried to see if we could apply it to balance sheet and to numbers contained in the balance sheet of each single firm in order to have an index of potential evasion at firm level. And we use data from the Bureau van Dijk AIDA database, which contains all the financial statements of Italian firms. And each financial statements contains 243 items. Obviously, this includes sub-items and totals. So we need to remove duplication and missing values before performing the analysis. And hopefully, we should have enough items left to be able to determine whether the distribution for that firm and that year is conform to Benford law. Here is an example for one firm, SNEM, located in Rome. And this is a firm that obtained a maximum score, a 3-star score, on the legality rating released from the Italian Authority for Competition and Market Regulation. Here in the plot, you can see a red cross indicating the relative frequency of observation for each digit. And in the middle of this green interval, you have the corresponding probability according to the Benford law. And in green, you have a confidence interval for this probability. And so you can see that all the crosses in this case are well inside the confidence interval, meaning that we have no reason to doubt about the fact that the data have not been manipulated. And in fact, if you look at the different statistics we've seen before, the p-values for these statistics are large enough, meaning that there is no significant deviation between the observed distribution and the theoretical one under the Benford law. This is a different case for another firm, SHEB, always also located in Rome. But this was recently accused of a criminal organization. And here you can see some crosses which are just on the border of the confidence interval, and one of them is outside the confidence interval. And looking at the p-values for the different statistics, now they are quite small, indicating a significant deviation from the theoretical distribution under the Benford law. So in this case, we might claim that data have probably been manipulated. Just to show you that this is a really simple analysis to perform. From AIDA, you can download data you can search, first of all, for firms, for just one firm or more than one firm. You can search by the name of the firm or some identification code, or you can, for example, search for firms having some specific characteristics. So, for example, belonging to a certain geographical area or involved in a certain production sector. Once you have selected the firms you are interested in, you can have access to their balance sheet, and you can download them in a worksheet file. So you can then perform the analysis using simply Excel, or you can upload the Excel file into a specific statistical software. I used R, which is a free software. And after some cleaning of the data, you can use one of the library in R to perform Benford analysis. There are different kind of libraries for doing this. I use Benford tests and the function signif the analysis to just obtain the plot I show you before. So going back to the problem of discovering tax evasion, we considered obviously a larger sample of firms, not just two firms, to determine whether Benford law has a good potential in discovering evasion. So we consider the population of Italian industrial, commercial, and service companies, and we just considered firms classified as active and established before 2015 to have enough years of financial statements to analyze. And we used a stratified random sampling approach in which the strata were defined by the 20 Italian regions and the 21 Ateco macro sectors of activity. So that at the end we had 420 different strata. And from each of them, we drew the 10% of the firms. And for each firm and each year, we computed the chi-square statistic. And we define a firm as non-compliant if the firm does not conform to Benford law in at least one of the years considered. On the other hand, we consider a firm as compliant if it conforms to Benford law in all the 8 years considered. And obviously, there are some firms for which we didn't have enough data in the financial statement to perform the analysis, so at least in some years. In this case, we consider the firm as non-compliant if it does not conform to Benford law in at least one of the years for which we could compute the chi-square statistic. And otherwise, we simply consider it as undefined. So the best way to determine the capability of this methodology to correctly classify firms as evading or not taxes would be to use labeled data. It means we would need a sample for which we know whether each firm did evaded tax or not. Obviously, these data are not available. They are sensitive data. So what we did is we aggregated data and try to see whether aggregated data were able to reproduce some well-known stylized fact about tax evasion in Italy, and also compare our results with other well-known proxies for tax evasion, and in particular with the synthetic tax reliability indexes, which are released by the Ministry of Economic and Finance in Italy, and they refer to each single economic firm, and they classify firms as reliable or not from a taxation point of view. So a first well-known stylized fact concerns the geographical pattern of tax evasion in Italy. It is well known that in the south tax evasion is more widespread and more systemic than in the north. And this fact is reflected by all the different proxies for generally used for tax evasion. It is also reflected by these ISA indexes. You can clearly see that we have a higher level in the center and the south compared to the north. And these are the results we get using the Benford law, which are very similar as absolute value to that provided by the ISA index, and reproduce the same pattern with higher values in the south and the island and smaller values in the north. This is in more detail at regional level. So here on the left, you have the percentage of potentially non-compliant firms according to our methodology. And here you have the percentage of unreliability according to the ISA index. And for example, we have 3 regions, Calabria, Basilicata, and Lazio, which are among the 5 more affected by tax evasion regions in both of the two ratings. We have also Friuli Venezia Giulia and Liguria that in both ratings are among the 5 less affected region. And we can also see Val d'Aosta, which presents higher level of evasion compared to the other regions in the north. So there is a quite high correlation, above 50% Pearson correlation between these two rankings. Another well-known stylized fact about tax evasion in Italy is that small firms have a higher propensity to evasion compared to large firms. Here we didn't have the aggregated data for the ISA index, so we are just considering the Benford law, what we got with Benford law, and you can clearly see that the percentage of non-compliance is decreasing as the size of a firm increases. So it seems that Benford law is able, the methodology proposed is able to reflect this particular pattern of tax evasion in Italy. And also tax evasion varies according to the sector of activity. So in this case, we have the data concerning the other indicator, the ISA indicator, and we can see that both the methodology reveal how agriculture is the sector more affected by evasion, and we've seen earlier this morning that is also a very affected sector from a more general point of view of fraud. And there are, this is followed by services and commerce, while manufacturing and professionals are less affected by tax evasion, even if their ordering, their ranking is different under the two different measures. So just to conclude, we believe that on the results we obtain, Benford law is a powerful instrument that can be used to address auditing and more in general anti-fraud efforts in combination with other instruments. And obviously the best way to check how reliable this instrument is would be to have labeled data, which we do not have. And this is why we use the aggregation and we compare the aggregated results obtained with the Benford law with those obtaining using other different index for tax evasion. I really thank you for your attention. Here is a bit of bibliography on the subject, and obviously I'm ready to answer any of your questions on the subject. Thank you.